Most serious discussions about these factors begin with the same prerequisite: liquid water.
All the searches that are being done for life elsewhere, their starting position is a terrestrial-class planet with water.
It is now widely recognized that the chemical properties of water are exquisitely suited for carbon-based life. These properties include water's ability to dissolve and transport the chemical nutrients vital to all living organisms, and its unmatched capacity to absorb heat from the sun, a process critical for regulating the Earth's surface temperature. In liquid form, water is an extraordinary substance, and its existence hinges upon another factor essential to complex life: a planet's distance from its home star.
It's like what they say in real estate: location, location, location. A habitable planet lives in what we call the Goldilocks zone. It's not too hot, it's not too cold, it's just right. And when I say just right, I mean just right for water.
Liquid water really helps define the habitable zone. If it's too hot, again, the water just boils away, you just can't get condensed water. It's too cold, as in Mars today, it freezes out.
Within our solar system, the habitable zone is relatively narrow, beginning well outside the orbit of Venus and ending short of the orbit of Mars. If the Earth were just 5% closer to the Sun, it would be subject to the same fate as Venus: a runaway greenhouse effect with temperatures rising to nearly 900 degrees Fahrenheit. Conversely, if the Earth were 20% farther from its home star, carbon dioxide clouds would form in its upper atmosphere, initiating the cycle of ice and cold that has sterilized Mars.
The presence of liquid water is a necessary condition for life, but it's not a sufficient condition. After all, there may be liquid water under the frozen surfaces of Mars and Jupiter's moon Europa, but there's very little chance that complex life exists in either of these places. You see, contrary to what the Copernican principle might suggest, the recipe for life is much more complex than just add water.
If a recipe for a planet capable of supporting complex life really did exist, then what ingredients beyond liquid water might be required? The list of necessary factors continues to grow.
We live on this paper-thin crust. If the Earth's crust were significantly thicker, then plate tectonic recycling could not take place.
The Earth's crust varies in thickness from about 4 to 30 miles. It consists of more than a dozen tectonic plates that are in constant motion. This dynamic geology regulates the planet's interior temperature, recycles carbon, mixes chemical elements essential to living organisms, and shapes the continents. Deep within the Earth's interior, the movement of liquid iron generates a protective magnetic field essential to complex life. If our planet was smaller, its magnetic field would be weaker, allowing the solar wind to strip away our atmosphere, slowly transforming the Earth into a dead, barren world much like Mars.
We need an oxygen atmosphere, and the oxygen-nitrogen atmosphere that the Earth has is necessary for complex life.
As seen from space, the Earth's atmosphere glows as a thin blue ribbon of light. Measuring less than 1% of the planet's diameter, it is composed of a mixture of nitrogen, oxygen, and carbon dioxide. As a result, our atmosphere ensures a temperate climate, protection from the sun's radiation, and the correct combination of gases necessary for liquid water and complex life.
For a size of planet like Earth, our moon is big. The current thinking is that if our moon didn't exist, neither would we.
1/4 the size of the Earth, the moon's powerful gravitational pull stabilizes the angle of its axis, at a nearly constant 23.5 degrees. This ensures relatively temperate seasonal changes, and the only climate in the solar system mild enough to sustain complex living organisms.
If we find life out there, especially complex or even intelligent life, it will be around a star similar to our own.
We orbit what is known as a spectral type G2 dwarf main sequence star. It is well suited for our needs. If the Sun were less massive, like 90% of the stars in the galaxy, the habitable zone would be smaller. To remain within its boundaries, the Earth would have to be positioned closer to its star. Here, increased gravity would lock our planet's rotation into synchronization with its orbit. While one side of the Earth continually faced the Sun and increased radiation from solar flares, the dark side of the planet would lay shrouded in perpetual cold and ice. It is unlikely complex life could tolerate these drastic extremes in temperature.
A lot of things went right on Earth to have yielded complex life, absolutely.
The number of factors that have been postulated has grown. Currently, the typical number you would see is, in a typical list, would have something like 20.
We find that we need to be at the right location in the galaxy, that we're inside the circumstellar habitable zone of a star, that we're in a planetary system with giant planets that can shield the inner planets from too many comet impacts, that we're orbiting the right kind of star that's not too cool or not too hot, that we're on a planet that has a moon that can stabilize the tilt of its axis, that we're on a planet that's a terrestrial planet, a planet that has a crust that's just thick enough that it can maintain plate tectonic activity, but it has enough heat in its interior that it's still circulating its liquid iron core so it can generate a magnetic field, that it has an atmosphere that has enough oxygen to allow for complex organisms to survive, that it has enough water and enough continents to allow for the diversity of life or an active biosphere that you need to support complex creatures such as ourselves. All these factors have to be met at one place and time in the galaxy if you're going to have a planet as habitable as the Earth, which you need for complex and even technological life.
In an attempt to estimate the probability of attaining this combination of factors simultaneously, some researchers have developed equations assigning a conservative 1 in 10 value to each factor deemed necessary for advanced life.
If every element has to be there at the same time, you have to multiply the probabilities. And that's what makes the probability at the end so small. You've got 10% of this and 10% of that, and these things rapidly multiply to exceedingly small numbers. The numbers on the order of 10 to minus 15, which is 1/1000th of 1 trillion. And it's a number like that you have to compare to the 100 billion stars that are in the galaxy. 100 billion is a very large number, but 1,000th of a trillionth is much, much smaller. On their face value, these probabilities are speaking. What they're telling us is this can't happen, or this is very unlikely to happen in the galaxy. And that's where the evidence is pushing us.
There are many probabilistic resources in the galaxy, but on the other side of the coin are all these factors that you need. You have to get just right in order to have just one habitable planet like the Earth. And that leads me to conclude that yes, we're rare in the galaxy.
While a growing body of scientific evidence may support this hypothesis, does the possibility that our planet is rare within the galaxy imply anything about its significance? Recently, astronomer Donald Brownlee considered this question in the best-selling book Rare Earth: Why Complex Life is Uncommon in the Universe.
There's a general feeling that nature wants to make Earth-like planets, and that naturally that life will evolve on them and naturally evolve to something like us. And yet the conditions, the environmental conditions on a planet that would allow more complex creatures similar to people or plants and animals is very rare. And so we wrote the book Rare Earth to point out that the Earth is actually a rather special place.
Brownlee contends that while relatively simple microbial life may thrive on planets throughout the universe, planets capable of sustaining complex life are exceedingly uncommon.
Well, the entire universe is highly hostile to life. If you compare all the known places in the universe, none of them compare to Earth. We live in a very special environment that provides what we need, provides air, provides food, stable conditions, so that the Earth is almost like a giant organism where its systems are interacting in a way that allows animals to survive. The real question is, why did this happen? Was it just a matter of luck or not? If you look at thousands of planets, only a small fraction of them, very small fraction, will be truly Earth-like. So if we are very rare, we did win the cosmic lottery. So we're a lucky planet. We're just in a very fortunate place.
When you consider chance as an explanation for a planet like Earth, you have to look at it in the context of the universe as a whole. While the odds appear astonishingly small that you'd get all the right ingredients to support complex life at this one place in the galaxy, you have to keep in mind that our galaxy is just one of perhaps 100 billion galaxies in the observable universe. Still, logically, I think you have to ask yourself, what if this convergence of factors didn't come about as the result of simply a cosmic lottery or a mere fluke or luck, but what if it's the result of some larger underlying purpose or design? And if the Earth does exist for a purpose, is there any way that we could tell?
On October the 24th, 1995, a rare natural phenomenon unexpectedly triggered a unique search for an answer.
Oh, look at this sky! It started with an experience I had in 1995. I went to observe a total eclipse of the sun in India. It was my first and still only total eclipse of the sun. It was a spectacular event. It's just an experience for all the emotions. Either astronomers who can understand the whole phenomenon and can predict it to within a second of time anywhere on the Earth, or a local native, are equally in awe and reacting in the same way to this incredible phenomenon. It really left a big impression on me.
For 51 unforgettable seconds, Guillermo Gonzalez and thousands of others looked on in wonder at this rare astronomical event. Gonzalez would later reflect upon both the mysterious beauty he had witnessed in the North Indian skies and the factors that had made it possible.
Fabulous! The requirements for producing a total eclipse of the sun are a luminous body, in our case the sun, an eclipsing body, in our case the moon, and then an observer platform, in our case the surface of the Earth, and they all have to be in a straight line in space. The apparent size of the moon in the sky has to be almost exactly the same as the apparent size of the sun in the sky. They're both about half a degree. The sun is 400 times bigger than the moon, but it's 400 times further away. So there's this coincidence people have noted for centuries, but they just say, oh, well, it's a coincidence, and shrug their shoulders.
As Gonzalez examined this rare alignment of sun, moon, and earth, he recognized the importance of these celestial bodies to the existence of complex life on our planet. The gravitational pull exerted by our moon, for example, is strong enough to regulate the Earth's climate by stabilizing its tilt and helping to circulate the warm and cold waters of its oceans, while our planet's distance from the sun permits both liquid water and an oxygen-rich atmosphere.
You have to have the right distance of the observer's home planet from its host star, and you have to have a large moon, and so there's this very strong overlap between the requirements for producing eclipses and the requirements for habitability, for having a planet that can support life.
In 1999, Gonzalez described this relationship between our survival and our ability to observe solar eclipses in the journal Astronomy and Geophysics. His ideas intrigued philosopher Jay Richards.
I've been focusing my research in cosmology, and in particular on applying probability theory to the fine-tuning of the laws of physics. I had a strong sense that this evidence pointed toward some sort of wider purpose to the universe. Then I read Gonzalez's work, and I had the same feeling that he did, that perfect solar eclipses were sort of the tip of the iceberg, the first instance of an entire class of evidence that provides a way for judging if the universe is the result of a fluke or some impersonal process or the result of purpose or design.